Okay, today we're going to finish up our Unit 7 lecture talking about how Gauss's law affects and is affected by conductive materials if they're placed into the electric field. So we're going to start with our where we always have been. We have this electric field, or make those plus charges rather than x's. Plus, 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 and we have a bunch of minuses over here. All right, and the electric field that goes in between them, okay, goes pretty much like this. A little bit of curvature to them, maybe. Make sure all your field lines have arrows on them. Okay, so here's our standard horizontal electric field. When we put a conducting material into our magnetic field, this is what happens. We get in our what kinds of materials tend to be conductors?
Metal.
Okay, metals, right? So in metals have, we're going to take you back to your metallic bonding in your chemistry a little bit. Metals have what's called the kernel, which is everything inside of the valence electrons, and those are pretty much by definition positively charged throughout your metal. And metal positives throughout, so every single atom of your metal has a kernel in it. It's going to be this positive charge, and then around the kernel you have your valence electrons. But in a metal, the valence electrons can be delocalized. And if you remember from your first year chemistry, I don't know if they talk about it in AP, but you have the sea of electrons that all of your kernels are kind of floating in. And they are all held together by the electrostatic charges of the kernels and the electrons. But all around these guys, we have our electrons, and they're moving all over the place. They are free to move and pretty much randomly all over, and it's because that these electrons are allowed to move randomly throughout the metal that we have the metallic properties. We have that it's ductile. We can hammer this into sheets, really thin sheets. If you have gold, it can be hammered into a sheet that's just a couple atoms thick, and then you put it on your ice cream and you eat it because you're an ostentatious person and you eat ice cream with gold on it just so you can say, I eat ice cream with gold on it. Oh, look, here's one of the most valuable substances known to man. Let's eat it. So, right, 'cause we're America. Right, we're Americans, and we okay. And of course, gold is completely hypoallergenic, and it is completely non-digestible. So when your body finishes with the ice cream that you just eaten, finishes with the gold, it passes right through your digestive system, and your poop tends to sparkle. Okay, it has, right. So, okay, so go try this. This is actually an absurd thing that I feel absolutely safe saying. Go try this at home. Go ahead, buy some gold leaf, wrap it up, wrap a scoop of ice cream in it, and then eat it, and watch what happens. Okay. So, however, when our conducting material is placed into an electric field, some interesting things happen. Actually, there are other metallic properties also come out of this, by the way. It's ductile, it can turn into wires. And because the electrons are free to move, they can conduct electricity because it's the flow of electrons that allow for, it's the traveling electrons that allow for the conduction of electricity. And because they're allowed to move, if they're placed into an electric field, well, our negatively charged particles get attracted to the positively charged side of the field, and we get a negative charge on this side of our conducting material, all over here, which means that our field simplifies. Instead of going from our positives all the way over here, we now have nearer negatives. And we get this more simplified field that stops here instead. But if we have all of our negative charge on this side, what does the other side of the conductor have to be? The other side of the conductor has to wind up being positive. So we start getting a positive charge over on this side. Okay, and our positive field starts to send out, because we always go from positive to negative with our electric lines. Okay, our positive starts to create its own electric field with the negatives that were somewhere else in the universe that was at the other end of our original electric field. Okay, so what does that mean for what's going on in here? Is there any electric flux from this electric field getting into the conductor? No, because it's stopping with the charges that are outside the conductor. Are any of these field lines, okay, here going back into the conductor? No, because these electric charges, these positive charges, are sending the field out to the negative on the other side, which means that inside our conductor, the electric field must equal 0. So if we have a conductor that is in an electric field, if you're inside the conductor, there is no electric field. None. And all of the charge goes to the outside of the conductor. Yes?
Where did the minus and positive, the protons and electrons come from outside the conductor? Is it present in the surface?
These here or these out here?
The one inside.
So these here, like these negatives. It's sort of like what happens with a dipole molecule, that if you have one end of the molecule that has a higher electronegativity, the electrons tend to spend more time around that one. That's sort of what's going on here, is that this positive electric field is pulling on the electrons to be on this side of the conductor.
Was it the surface?
Which no, they were anywhere. They were throughout the conductor, because it was electrically neutral before. Okay, and then it creates an instant of motion of particles to create the charge out on the outside. But the amount of charged particles, amount of electrons on this side of the conductor, is going to be proportional. Depends on the strength of the field.
So the ones inside, like the electrons and the protons, all the way went to the surface, and then.
Yeah. Well, the protons don't move.
Yeah.
The protons don't move. The kernels stay where they are. The kernels stay where they are. They don't move around. Okay, but what happens with the electron? What is a positive charge when we're dealing with our materials? A positive charge it comes from the protons, but how do we generate one? It's generally from the loss of electrons, right? So if there's an even charge distribution throughout this whole thing, then all of a sudden we have a motion of the electrons to the other side. This side is now with a lack of electrons, which generates the positive charge. Okay, and then those create the field lines to the. Yeah. Okay. So inside the field, it must equal 0, but this only happens when we have electrostatic we must have electrostatic conditions. There must not be a current flowing through the conductor. If there is, then we have all sorts of other issues, and we have a moving electric field, which we will learn very soon creates a magnetic field, and then we start getting Maxwell's laws and dogs and cats living together and mass confusion. Okay. Okay. So think about this. If all E must equal 0, that also means that all charge is at the surface. That says charge, even though it's written horribly ugly. All right. So think about. Okay. So think about a sphere. Right. So if we have a positively charged sphere, okay, on a conductor, okay, all of these are going to have their own little. They're all going to have their own electric field coming from each individual particle. But then what results is, if this is a conductor, then our charges move so that we have all of our charge concentrated at the surface. And inside, well, we've seen this before, right? If all of our charge is at the surface, what's the electric field like in here? Right. It still equals 0, but we discovered this. Even if it's an insulated surface, the electric field is still 0 if all of the charges are on the outer surface, right? And it creates an abundance of negatives inside. But that's not so important. Okay, so what is then E just outside of a conducting surface? What is the electric field just outside of a conducting surface? So here's a whole bunch of positive charges again. Oh. Okay, so yes, there's a general curve to this. Okay, so we have okay, and if we are just outside, okay, then we have a dA right here. Okay, and we have a surface above. All right, we have electric field above. So like, let's do our cylindrical. If we get close enough, it acts like a plane. Okay, it acts like a plane plane symmetry. So we have our A here, and this is equivalent to A on top, and so the flux going up is equal to that A. But do we have any flux going inside? If this is a conducting surface, there's no, the field inside the conducting surface must be 0, so there is no flux. There is no flux inside the sphere. So, what's going to be our field? Well, we have Q enclosed over epsilon. And if this has some surface density, some charge density on the surface of sigma, okay, because it's an area charge density, that our Q enclosed is just going to be sigma times A, right? All right, whatever the charge density times the area that we're looking at, and that's going to equal our uniform field here. So E A, whatever our A is that we're looking at, is going to equal sigma A over epsilon naught. Well, look, the A's just cancel, and so our field equals our area density over epsilon naught. And that's it. That's the strength of the field right there. It's just the charge divided by, or the area charge density divided by epsilon naught is going to be our strength of our field for a charged conductor. And that's about it.
So is that like the only thing that's different about this and the other thing is that this one, the only thing that goes is one side.
Right, okay, so what we talked about at lunch. Okay, so I want to draw a comparison here, and this is actually back to the charged plane that we talked about yesterday. This is a charged plane. This is an insulated surface, and so we talked about having half of our if this area above is 1A and area below is 2A, guys, all you guys tune in here. I want you to understand this conceptually. Half of the other half of the charge is centering field lines up, right? It's got. Okay, so we look at this that we did yesterday, compared to this value that we found today, and this should make some sense, because if our electric field is going to be our area charge density over 2 epsilon naught, really this means is that this is 1/2 of sigma over epsilon naught, because we have half of the charge. If the sigmas are the same, then half of the charge is putting field down, the other half is putting field up, right? But if we have a conductor, then the field is parallel and is unidirectional. It's only one direction. It's not sending any of this field down. And so it's not splitting. We don't have any flux this direction. So all of the flux is going up, and so we don't have to divide by 2. We're not dividing our field into 2 portions. It's all in one direction. So with a conductor, near the surface, it's just sigma over epsilon naught. Okay, and it's analogous to a charged plane, except this time the charged plane has flux in both directions, and so we have to account for the area on the backside, which reduces the amount of electric field that we have on either particular side of the plane. Does that make sense to you guys? Okay. Okay.
What happens if your cylinder went all the way through? What if it went all the way through it? Yeah. Would it be what happened?
Well, remember what's happening on the other side of the conductor. The other side of the conductor is negative, 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 right? And field lines are going in like this, right?
Positive all the way around.
Is it positive all the way around, or is it positive on one side and negative on the other side? I'm confused.
If this was a conductor that had a total positive charge on it, and you went all and it went all the way through, then it would just be like then you would be back to here if you're taking a total, if your cross-sectional areas are the same. If you're taking a cylindrical section, I mean you're talking a pretty fringe experiment here. So let's take a cylindrical section here that goes through the sphere, right? Okay, well, this area here, the flux coming out is going to equal the flux coming out there. Okay, and so you just wind up in this situation again, but with the math a little more complicated. But you're not going to see the purpose for demonstrating this was to show near the surface.
Oh.
Okay. What is it near the surface of your conductor, and then it's just your epsilon, sigma over E naught over epsilon naught. Okay. Sean?
Like in the book it says on an irregularly shaped conductor the surface charge density is greatest at the location where the radius is the smallest.
Mm-hmm.
Is there an equation that accompanies that? Like, or is it just constant? Is there like question?
Well, let's draw that here, because okay, here's our irregularly shaped object, right?
That's a conductor?
And where the radius is the greatest on a conductor, it's where the radius is the smallest. Okay, so I need to make one with a more distinctive. Okay, the field, the individual effects of the charges are going to repel each other more, and so
Is it because like E equals something over R squared?
well,
You have it over.
I have to be honest. I'm gonna have to look that one up because this is not meeting the conditions that we started with when we started analyzing this stuff, which required a high degree of symmetry. There's not a whole lot of symmetry here, so I would need to look deeper into that to answer that question. Okay, so now that we have that, and my infallibility is now on permanent record, we can stop this video.